start with week 11 session. So today I'll be discussing about turbines, and first let us discuss what is the difference between an axial compressor and an axial turbine. So if you notice that most of the diagrams will have this condition where you have a compressor, and usually you'll see that the thickness of this compressor is much larger. It is drawn much larger than the thickness of the turbine. So what that essentially represents is that the number of stages in a compressor is much more than that in an axial turbine. And also what we would see is that in a compressor, the blades, the turning angle of these blades is much lesser, whereas in turbines the blades are really twisted and they are turned through a larger angle. So if I have to recapitulate what I said, the number of stages in a compressor are much more, okay, and they are less in a turbine. The turning angle of blades is less in the case of compressor but more in the case of turbine. And the simple reason here is that in a compressor the flow is moving against the pressure gradient. So there is an adverse pressure gradient. Okay, and in turbine there is a favorable pressure gradient. So when there is a favorable pressure gradient, then the chances of flow separation that reduces. Okay, so remember that compressor is actually, it is compressing the air, so pressure is increasing, and now the flow has to move against this increasing pressure. Right? That is what we mean here by adverse pressure gradient. And in a turbine the flow is actually accelerating, pressure is decreasing, so the flow can very easily move in that direction. So as a result, what we can do is we can turn the flow by a large angle, and in each stage of the turbine. So what is a stage? A stage is a stator and a rotor combination. So in each stage of the turbine we can achieve more pressure drop. In each stage of a compressor we can achieve less pressure increase. So that is why in one stage of a turbine you will see that each of these stator and rotor blades are turned by a large angle, as you can see over here. And then you can also see that here as you move from the stator from one end to the other, you can see clearly the area is decreasing, so velocity will be increasing, which is what happens in a turbine. Okay, so now we can draw the velocity triangles over here. So how would the velocity triangles look? So let us see. So first there is a flow which is coming into the stator, and stator, it stays stationary, it is not moving. It is the rotor which is attached to the hub and that is rotating, right? So whatever the stator will see, that is going to be the absolute velocities, and when you sit on the rotor and see the flow, then what you see is the relative velocities. So the flow that comes into the stator, it should come like in this direction, right? So this is going to be the absolute velocity, and what is going to leave will be leaving in somewhat this direction, and that also is going to be an absolute velocity. So I can call this as C1 and this as C2, and then what is going to enter the rotor is actually this C2, right? But then remember that the rotor is actually turning, right? So let us assume that this rotor is turning by turning in this manner, right? So there is a rotation, out of the page rotation, right? So that is denoted by the blade speed u. And now the relative velocity can be understood, because see, relative velocity has the relation that uh, if you have this blade velocity and this is your absolute velocity c2, then the relative velocity w2 is going to be like this, right? So c2 plus u is w2. So here w2 is the relative velocity which the rotor will see at its inlet, and what is going to leave is w3. So you can draw it like this, w3, and as a result of this relative velocity there will be an absolute velocity of c3. Now an ideal design, okay, so in an ideal design, what do we want? We want that C1 should be equal to C3, because whatever was the inlet to this stator should be inlet to the next stage stator, right? So we want same conditions at each stage. So same condition at each stage, right? Okay, so we can now compile this entire velocity triangle, and let us draw it. So let's say this was my blade velocity u, and so there was an incoming flow. So I'll draw the inlet triangle first. So this is C3, but C3 is equal to C1, right? So I'll write it over here, C3 is equal to C1 anyways, and the relative velocity is now going to be W3, right? So I'll call this W3, and we can also demarcate these angles. So this is the absolute angle, okay, and this is the relative angle. So the absolutes will be denoted by alpha, relatives will be denoted by beta. Okay. And now let me draw the outlet velocity triangle. So what happens in a stator? We saw that velocity is supposed to increase, right? So C2 will be larger than C1 or C3. So in this case you will see that the vector C2 is going to be much larger than C3. You can see here by the length itself, okay. And what is happening in the rotor? So ideally you will see that, okay, if you see in the absolute frame, you'll see C2 is decreasing to C3, right? But in the rotating frame, again the velocity is actually increasing, okay. So what came into the rotor was W2, which is this, and if you compare it to the outlet velocity, relative velocity W3, you'll see that W3 is more than W2, right? And then we'll denote these angles again. This is going to be alpha 2 and this is going to be beta 2. And then in the lectures you must have also seen different type of turbines, like you have impulse turbine, then 50% reaction turbine, and there is the condition where you have zero swirl in the turbine. So for all these conditions the velocity triangle will change slightly, right? So for example, in a 50% reaction turbine the velocity triangle becomes symmetric. So yeah, you can refer the lectures for these velocity triangles. So I'll move on to the questions for today. Okay, the first question is, according to the velocity triangle of an axial flow turbine, which one of the following options is true? So is the relative velocity and axial velocity components at the outlet higher than the inlet? So we just now saw that at the outlet, which is station 3, and we are comparing it with station 1, they are asking if the relative velocity and the axial velocity components are different. Well, that's not true. We are trying to ensure that the axial velocity remains same throughout the stage. So Cz. So what is Cz? That is nothing but your C3 cos alpha 3, but it is also equal to C2 cos alpha 2. Okay, so this this length is Cz, and that axial velocity component, it remains same throughout. So this option is not right. Relative velocity component at the outlet is lower than that at the inlet. No, we saw that W3 is actually more than W2, isn't it? So this is again false. The absolute velocity component at the outlet, so absolute velocity at the outlet is C3, is lower than the inlet, and the blade speed remains constant. Yeah, so this is right. Okay, so this is the correct answer. The wall velocity component remains constant. No, that is not true. Okay, so I'll just highlight the answer is this option. Okay. Question 2. In the case of axial flow turbine, blade loading coefficient is a function of what? So what is blade loading coefficient? We know it is this value psi, which is defined as delta h naught by u square, right? So you're basically rotating the shaft, which is rotating these rotor blades. That is the amount of work that you are providing, and it can be quantified by u square. And then you are basically asking how much work is done by the rotor on the fluid itself. So that is this ratio psi. Now the question is, the psi is a function of what? So psi is going to depend on the flow velocities, right? And it is also going to depend on the blade angles. So if you see the formula, this turns out to be something like C2 theta minus C1 theta divided by u. Okay, and then you can further simplify this and write that this is Cz by u, but you know Cz by u is nothing but your flow coefficient, and this multiplied to tan alpha 2 minus tan alpha 1, right? So from this formula you can see that the answer is psi depends on flow coefficient and blade angle. Okay, so I'll again highlight this answer here. Okay, then next is for an axial flow turbine, the absolute velocity, does it increase or decrease from inlet to outlet of the rotor? So let's go back to this velocity triangle. So at the inlet of the rotor, W2, at the outlet it is W3. So relative velocity is increasing, the absolute velocity is decreasing, right? So here the answer is, they have asked for absolute velocity, so the answer is decreases. Okay, so next the question is about radial turbines. Now what happens in an inlet flow radial turbine? So here what you can see in this diagram is a radial turbine, and the flow comes in the radial direction and it is thrown out in the axial direction, right? So now the question is, for the inlet velocity triangle of a 90-degree inward flow radial turbine, the whirl velocity component is equal to which of these following? So whirl velocity component is the tangential component, right? But remember, in the like I said, the flow is coming in this radial direction, right? And then it is being thrown into the axial direction, and the flow is also the blades are also being rotated in this manner, right? So the tangential velocity of the flow and the tangential velocity of these blades, the blade velocity is going to be the same. So here the answer is blade speed. Okay. Then which of the following is correct for flow through the 90-degree radial turbine? So so you can see from the diagram also here that first the flow comes in, like we said, comes in the radial direction, so it will come inwards, like in this direction, so it will come through the volute. So we start with the volute, then is the nozzle. So there is this nozzle, then the rotor, then diffuser. So the answer here is the first option, where there is an inward flow from the volute to the nozzle, then to the impeller, which is the rotor blades, and then it is exhausted in the diffuser. Okay. Then the next question is for a 90-degree flow radial turbine, the flow through nozzle ring leads to so how does that change the total pressure? So what is happening in a nozzle ring? Nozzle ring is nothing but a stator, right? So in a stator, there is no work being added, no heat being added, nothing is happening over here. So ideally the total pressure should remain same, but there will be losses because now you're turning the flow, making it from radial to axial. So there are going to be losses for sure. So we understand here that the total pressure is going to decrease. The only chance where total pressure can increase is when there is any work being added to the flow, right? So this is decrease in total pressure. Okay. So now we'll move on to a numerical question. So the following data are given for a single stage axial turbine with a free vortex. Now what is a free vortex design? So you would know this free vortex design is where r c theta is equal to a constant. Okay, and the consequences of this free vortex design is also that at the mean radius, so at mid radius, let me denote this mid radius as rm, the degree of reaction, right, degree of reaction is 0.5, and also the flow coefficient Cz by u is 0.5. Okay, so this is the implication of a free vortex design. So now what is given to us? We are given the total head inlet pressure. Remember, I'll just redraw here that you have a stator. Okay, so this is your first stator blade, and then you have a rotor blade. So this is station 1, station 2, and then you have a station 3 over here. So what we are given is the total head inlet pressure, which is nothing but P naught at station 1, which is the head position, right? So this is given to be 6.5 bar, and we are also given P1, the static head pressure at mean radius. So we are calculating everything at the mean radius Rm. Okay, and P1 is given to be 1.7 bar, right? And we are also given T01, which is 900 Kelvin, right? So now we can easily find T1. So let us use our isentropic relations, and we know P01 by P1 is equal to T01 by T1 to the power of gamma by gamma minus 1. And if you note here that gamma is given to be 1.33. Okay, so if we plug in these values, right, so what do we get? T01 by T1 turns out to be 1.3948. okay, and again you can put the value of T01, so that gives you value of T1, and T1 is nothing but 645.25 Kelvin. Okay, so now what we need to do is, we are given these quantities, pressure, temperature, but we have to find the velocities and the angles, right? So we have to basically convert this problem from your thermodynamics to the velocity triangles. So how do we do that? So if you note, we have this relation that T naught by T is actually 1 plus gamma minus 1 by 2 m square, right? And if you further simplify this, actually in the very beginning of the derivation of this formula, you get this thing that T naught is actually equal to T plus C square by 2C. Okay, so this is the formula we need to remember. Okay, and this is what I'll be using over here. So we know T naught, we know T at station 1, so we can easily find the velocity, inlet velocity at station 1, right? So if I use this at station 1, Okay, so that gives me C1. So Cp is also given to you over here. Cp value is 1.147 kilojoule per kg Kelvin. So if we plug in all these values, C1 turns out to be 764.45 meter per second. Okay. Okay. Now comes the part where we use the concept that this is a free vortex design and the degree of reaction is going to be 0.5 and also Cz by U is also 0.5. Okay, so what is the condition for 50% reaction turbine? So 50% reaction turbine, if you draw the velocity triangles, it looks something like this. So let us say this is my blade velocity, okay, and let us say that there is an inlet velocity of this in this direction. So this is C3 or C1. Okay, and this is my W3. Okay, so because of the symmetry of the problem, now what will happen? Let us say this was my this was alpha 3, right, or alpha 1. So in this case, because of the 50% reaction turbine, when you equate R is equal to 0.5, you will get a condition that alpha 3 is actually equal to beta 2 and alpha 2 is actually equal to beta 3. What is beta 3? Beta 3 is this angle, right? So now if I draw the other half of the velocity triangle and use another color, so this is going to be a symmetric looking thing. Just that what is the length of W3 would be the length of C3. What is the length of C3 over here will be actually the length of W2, and this angle is beta 2 and this beta 2 angle is equal to alpha 3. Okay, so now I can also write this blade velocity is nothing but, if you see, if I take this component, this is C2, I take the component of C2 along this blade velocity, that is C2 theta, right, and that minus this length, but this length is equal to this length, right? So I am going to subtract from C2 theta, I am going to subtract C3 theta, and that will give me the blade velocity. Okay, so this I can further write as Cz into tan beta 1 minus Cz tan alpha 1. Okay, and what is Cz again? So Cz is this length. Alright, now if we go back to the question, we are given this nozzle outlet angle. Nozzle is stator, so outlet angle with respect to stator is going to be the absolute angle, that is nothing but alpha 2. So what I am given is alpha 2 and also I am given beta 3, so this is nothing but 65 degrees. So using this, what we can do is we can rearrange. This is U by Cz, but we know Cz by U is 0.5, so this is nothing but 2. Okay, and this is equal to tan minus tan alpha 1 and tan beta 1 or tan beta 3 I can write as tan alpha 2, right? So this is plus tan alpha 2, and now I know alpha 1, so I can find alpha 2. So if you just solve this equation, you will get, so alpha 2 is known 65 degree, alpha 1 you will get is equal to 8.22 degree approximately. Okay, and then I know Cz can be also found as C1 cos alpha 1 and that is equal to C2 cos alpha 2. So now I know C1, I know alpha 1, I know alpha 2, so I can find this quantity C2, right? So plug in all the values, this gives me C2 is equal to 1790 meters per second. Alright. And also now what you can do is you can find CZ. So you can also find blade velocity U. Okay, so if in the question they ask what is the blade velocity, you can solve from here. So therefore I'll just give a hint here. In a case where the question asks you to calculate blade velocity, you can find CZ equals C2 cos alpha 2, then find U, which is nothing but 2 times CZ. Okay. Right, and then we have to find the static temperature at inlet of rotor, which we have done. Yeah, so at the inlet of the rotor, we can write this equation T02 is equal to T2 plus C2 square by 2C, right? And now we know C2, and by the fact that there is no work done by the stator, T01 will be equal to T02. Hence, we can find T2. Okay, so this was given to us as 900 Kelvin. So you can just plug in the value and find the value of T2. Okay. So what I'll do is I'll move on and show a solution to one more numerical. This is a numerical that it's a solved example in one of the textbooks. It's an interesting problem. So let us just see how to calculate. Let us say that we have this free power turbine of an axial gas turbine, and the total work of this turbine is given to us, that is 1000 kilowatts. Okay, and this is operating under the following conditions. So they have given the limiting tip speed. So why do we need a limiting tip speed? Because at the tip of the rotor there will be a maximum speed that is allowed, because anything beyond that speed then there will be shocks created at the rotor place, right? So there is a limiting speed. Then there is a hub tip ratio given, inlet stagnation pressure is given, inlet stagnation temperature is given, right? So P01 is given, T01 is given. Outlet static pressure is given, so let me call this PE. Axial exhaust direction. So in the exhaust direction there is only an axial component, there is no tangential component. So what this condition essentially gives us is that there is zero swirl, right? Because the swirl velocity, the whirling velocity is 0. Okay. So C theta exit is 0. Alright. Then there is also 50% reaction at mean diameter. So R is equal to 0.5 at RM. This is given. Okay. Axial velocity ratio 0.5 at mean diameter. Alright. And then same velocity triangles for all stages. So this again implies that C1 is equal to C3, right? What we discussed earlier. And then we have to find what is the number of stages required and the rotor inlet and exit angles at the mean diameter. So how do we do this? Let us start by noting all the quantities that we have. So P is equal to 1000 kilowatts. This is the power, right? The tip velocity is 400 meter per second. And P01, T01 and PE is given. And the axial velocity ratio, which was CZ by U, is 0.5. Okay. So now we can write this. Total work, that is by the entire turbine, by m dot is equal to delta H naught, which is nothing but Cp T naught inlet minus T exit, right? And I can just rearrange this and write Cp T naught inlet 1 minus Te by T naught inlet. Alright, and I can find this Te by T naught inlet as Pe by P naught inlet whole to the power of gamma minus 1 by gamma. So now if you see the question, they have given you Pe, they have given you P naught inlet. Okay, I think I should write this consistently. This is P naught inlet, T naught inlet. Okay, so and gamma value is also given to you. Okay, here it is not given, so let us say I'll let you assume that gamma is 1.33. okay, alright, so if you just plug in all these values, you can find delta H naught. So the value of delta H naught turns out to be 238.7 kilojoule per kg. Now for one stage, the work can be found separately. See, this was given to me as the total power for the entire turbine. Now I can find for one stage. So for one stage, work by m dot, right, is nothing but delta H naught for that stage. And because for all stages it is same, so I'll just calculate it for one of these stages, which is U into delta C theta. Okay, and also we know that because this is a 50% reaction turbine, right, so this is a 50% reaction turbine and there is zero swirl. So for all these conditions, we know that at mid radius, U is actually equal to delta C theta, right? So because we know this, I can now plug it back here and write this is nothing but U square. Okay, now what are we given? Are we given U at the mid radius? No, but we are given U at the tip. So okay, I know U at the tip, I know radius ratio of all the radii. Okay, so I can write this equation that ut is actually RT into let us say the speed of rotation, right? So this is the rotation speed, omega, right? So this is for rotation, so this is going to be RT omega, and at the mid radius, U is equal to this mid radius Rm into omega, right? So we know what is the hub to tip ratio. What I am given over here is RH by RT. Okay, so this is, I'll say RH by RT. But what do I want? I want Rm by RT, right? So I want UT by U is equal to RT by Rm. Okay, which I can write as so what is mean radius or mid radius? It is nothing but RT plus RH by 2, right? And on top I have RT. So if you just simplify this, you'll get okay, this is 2RT by RT plus RH, and this is nothing but 2 by 1 plus RH by RT, and this quantity I know, and I also know U tip. Okay, so hence we can find U at mid radius, right? This value turns out to be 320 meters per second. So this is very simple calculation, you can check that out, and then you can calculate what is delta H naught for that stage. Okay, and this is equal to, like we calculated earlier, um square, and this is nothing but 102.4 kilojoule per kg. So now we know the work per stage, and we also know the total work by the turbine. So now we can find what is the total number of stages actually required in this particular turbine, right? So number of stages is equal to delta H naught for turbine divided by delta H naught for one stage. Okay, so this, if you see, was 238.7 by 102.4, which is approximately 2 point something something. So you can say that you'll use either 2 or 3 stages. Okay, so your design should be about 2 or 3 stages of rotor stages. Okay, then the next part of the question is to calculate the rotor inlet and exit angles at the mean diameter. Okay, now what is the velocity triangle for the case where there is zero whirling velocity at the exit, that is zero exit swirl. So if there is no swirl, that means there is no c theta, so everything is going to come out axially. So at the exit, right, at exit of the stage, at exit of your stage, basically I should have this c theta component should be 0, right? So if you draw the velocity triangles now, it will look something like this. So this is my blade velocity u, okay, and there was, let us say, this inlet velocity c1, like and obviously the relative velocity is going to be this w1, and because there is no see, this is the tangential direction, so there is no tangential direction at the exit, only axial direction, right? Only axial direction, so it is going to be like this. This is w2 and this is c, right? Okay, so if you see, c2 theta is actually equal to u, and w2 theta is actually 0, right? Okay. Okay, so now the beta 2 angle is basically 0. So we can write the flow coefficient Cz by u. So if you see the formula, in that, the moment you put beta 2 is 0, you will get that Cz by u is nothing but 1 by tan beta 3. Okay, over here is tan beta 1. And at the mid radius, now we have this u mean velocity is known, or Cz by u is also known, it is 0.5, right? So just put this value, this is 1 by 2. So what does beta 1 turn out to be? It is tan inverse of 2. So this is beta 1 is equal to 63.40. Okay, so that's all for today. This is these are some sample problems on axial turbines.